Continuing on with this lesson on inverse trigonometry and calculus, you can remember this is 7.6. We left off with example 5, but we're going to pick back up now, needing to review the derivative of inverse secant. You will have a very strange form, 1 over u, radical u squared minus 1, also in the denominator, then times du dx. So as we come right here, you can see that f prime is going to be, and our u, by the way, is really the cube root of x. The cube root of x is really x to the 1/3. And it's probably easier to think of it that way, because then we'll have 1 over, and we'll have our u, that's our x to the 1/3. Then we'll have our square root of u squared, so here's x to the 1/3 squared, minus a 1. You can see we're just following this template. Then we're going to multiply through by the derivative of u. The derivative of x to the 1/3 is 1/3, and then we'll have to subtract a 1. This will become x to the negative 2/3. Well, cleaning this all up, you can see pretty quickly that we're going to have down below a 3. We'll have this x to the 1/3, but we'll also have x to the negative 2/3. That's going to bring this x to the 2/3 down right here. When I square x to the 1/3, I'll get x to the 2/3 inside that radical. And just cleaning this all up, x to the 1/3 times x to the 2/3 is just an x itself. Then inside we'll have x to the 2/3 minus a 1. Then taking a look at the derivative of inverse tangent, well, just coming back up here, you can see that the derivative of inverse tangent will be 1 over 1 plus u squared, and then the chain rule du dx. So as we continue taking a derivative here with f prime, we'll have 1 over 1 plus our u squared, so here's our 3x minus 5 quantity squared. But then if this is our u, the derivative du dx, derivative of 3x minus 5 is simply a 3. So this is considerably shorter. Just bring a 3 up on top. And you certainly do not have to expand this out. Perfectly okay to leave your answer just like so. Of course, after reviewing some derivatives, you might wonder if we're also going to have integrals. And indeed we are. In all truth, we're really going to narrow our focus to just these 3 theorems right here. If I gave you the integral of 1 over radical a squared minus u squared, that will simply be inverse sine of u over a plus c. For number 2, if I gave you 1 over a squared plus u squared, that would be 1 over a times inverse tangent of u over a plus c. And finally, if we are integrating 1 over u radical u squared minus a squared, that would be 1 over a inverse secant of u over a plus c. What is super important for you to notice is that number 1 does not have a 1 over a out in front. This is not a typo. This is, in fact, the one of the 3 inverse trig integrals that does not have a 1 over a out in front of it. Normally, I would go ahead and do a proof of at least one of these, but again, trying to streamline the lesson for the video, take it on good faith that this is true. You can see a proof in our textbook, or I'd be happy to provide one when we see each other in class. But let's take a look at example 8. For example 8, just recognizing the form, I hope example 8 is definitely looking very much like the inverse tangent form. So let's rewrite that to make it look a little bit nicer. 16 is really 4 squared. And really I'd have an x squared. That's like my u squared. And if that's the case, we can pretty much notice that our a would be equivalent to a 4. And our u, of course, would be equivalent to an x. And if that's the case, this integral would become 1 over 4 times the inverse tangent of x, which is my u, all over 4 plus a constant. And that would be sufficient. That would be fine. You can always double check if this is the correct work by taking a derivative. You would in fact eventually arrive at 1 over x squared plus 16. For number 9, you certainly don't have an inverse tangent here. If anything, it might look most closely to number 1 up above, where we're going to have an inverse sine. And that is, in fact, what we do have. Let's first notice that our a would be a 2. That would be 2 squared. And then we'll have our x squared squared. And why do we write this? Well, it's to help us out in finding a u substitution. We could let our u in this regard be x squared. And this is done deliberately with these theorems, using a u there. So very often we will need a u substitution. Let's see where we're going. Du would be 2x dx, and it quickly could be confirmed that dx is du all over 2x. Just cleaning this up real quickly. You could see we still have our 2 squared here. Now I have a u squared, but my dx would be du all over 2x, and this x would cancel out. In other words, we could rewrite this as pulling that 1/2 out. This is 1/2 all over the square root of 2 squared minus u squared du. Now, rolling back up to the top of the screen, if you have this as a setup, you just have inverse sine of u over a. So I could very quickly say I've got the inverse sine of u. Now my a, of course, is a 2 here. We already saw that up above. And then we'll just say plus c. Now, of course, to finish this up, we should resubstitute in that our u is really x squared. So we'll have 1/2 inverse sine of x squared over 2 plus c. Please do notice that, yeah, I do have a 1/2, but that 1/2 came from when I substituted in from dx. It didn't come from the antiderivative, when I was taking theorem 1 into play. When I had the 1 over radical 2 squared, down below, just as we saw, minus u squared, that's where I just had inverse sine of u over 2. Okay, to wrap this up, number 10 probably looks the most strange, and by far it is. It would look most similar, actually, to inverse secant, but no doubt about it, it probably looks rather strange. You can look right here and see for number 3, we'd have the integral of 1 over and a u squared minus a squared inside the root, and then a u. Let's see if we could perhaps clean this up just a little bit and maybe get just a tad bit of help. You'd say, well, what's being squared? Well, x squared. And the 9 here is really a 3 squared as well. And so my a would be a 3 here. My u certainly looks like it's x squared, and it is. Du would be 2x, and then we'd have a dx. And as we would solve for dx, just as we did up above, we'd have du all over 2x. And at first glance, this is probably going to be very upsetting. It's going to seem like something went terribly wrong. You see, because x squared squared will have u squared. We'll have our minus 3 squared right here. But the dx is really du all over 2x. And I think it's at this point where many students get very upset. They'll be convinced that something went wrong, namely because they're going to notice that the x's do not cancel. And this is going to be the case for an inverse secant integral. First of all, notice we do have that 2 down there. We can pull the 1/2 out. And it is definitely true that the x's do not cancel. In fact, they become x squared, in fact. And what is painstakingly obvious at present is we have more than one variable inside of our integral. And this can be very, very upsetting, but I want to point out to you that really x squared, as we substituted in the very beginning, was really just what we called u. Now it's at this point when you resubstitute that in, and you'll have to do that for this type of a problem, where you can now look back at your notes and say, well, wait a minute, if we go back to bullet point 3, aha, I've got that 1 over u, I've got a u squared and a minus a squared inside that radical. Now things are looking better. Now things are finally looking the way they should. And if we just follow that template, we could say, well, I'm going to have a 1/2 out in front, but I need 1 over a, I need 1 over 3. I'll need inverse secant of u over a, and then we'll say plus a constant. So this becomes 1/6 inverse secant of u over 3 plus a constant. But remember what u really was representing. U is really filling in for x squared. So we'll have 1/6 inverse secant of x squared over 3 plus a constant. So that's the most tricky of these integrals. But hang in there, keep working hard, and wish you the best.